Hi everyone, my name is Junming Chen. In this video, I will present our paper, Federated Domain Generalization for Image Recognition via Cross-Client Style Transfer. This is a joint work of HKUST and CUHK. Here is our motivation. First, domain generalization in federated learning setting is critical in many real-world scenarios. For example, it is important that a diagnosis model trained by multiple hospitals can be directly utilized in another hospital. Second, federated learning brings new challenges to domain generalization. Many domain generalization methods require centralized data from different domains, which violates the distributed and local requirements of federated learning. Moreover, directly aggregating local models may lead to a suboptimal global model. Next, let me introduce the background and our problem setting. Federated learning is a distributed machine learning framework trained on multiple clients, in which data sample exchange among clients is prohibited to protect privacy. In domain generalization, we train a generalizable model on data from one or more domains so that the trained model can perform well on an unseen domain. For our problem setting, we regard each client in federated learning as a domain, and we use Fed-average as the base federated learning framework in our work. Here comes our method, cross-client style transfer. There are 3 steps for our CCST method. The first step is local style computation. Each client computes their local styles and upload them to a global server. There are 2 types of style modes with corresponding mechanisms. The first one is single image style mode, in which we only compute a subset of image styles in each client and then upload them to the server. The second is overall domain style mode, in which we compute the pixel feature statistics for all the images in this domain, and each client only upload 1 style vector to server. The second step is server-side style bank broadcasting. The server gathers all the styles of each client as a style bank and broadcasts the bank back to all the clients. The third step is local style transfer, in which each client augments their own local data by transferring styles from other clients to local images. In this way, each client will have data with all the styles. So why does it work? From the figure, we can say, before CCST, the data distribution of each client is different, and local models tend to bias to different distributions. While after CCST, the data distribution of each client becomes similar. Therefore, each local model will learn to fit such similar distribution. We achieve state-of-the-art domain generalization performance on the federated learning setting on 3 public datasets. Note that we cannot directly compare with COPA due to the different experimental setting and availability of their code. Our method is also orthogonal to many other SOTA of the domain generalization methods. Therefore, CCST can be readily applied to those domain generalization methods to have a further performance boost. The diversity of our CCST can be controlled by a hyperparameter K. From the table, we can see normally larger diversity level leads to better generalization methods performance. We also give an intuitive and experimental analysis on the privacy-preserving performance of our style vectors. The results demonstrate that one can hardly reconstruct the original images merely from the style vectors using the generator from a SOTA GAN in FL setting. Thanks for listening. For more details, please refer to our paper and project page.